In Program 2, we examine the sp3 hybridization of carbon's orbitals and electrons. In the case of methane, the hydrogen orbitals overlap with carbon's hybridized orbitals to form 4 covalent bonds. These bonds are called sigma bonds, and sigma bonds are relatively stable arrangements. Carbon bonds to a variety of atoms, including other carbon atoms. This is the structural formula for ethane. The carbon-carbon sigma bonds can be visualized taking place in this manner. 2 carbon sp3 orbitals overlap, while the remaining sp3 orbitals overlap with hydrogen to take on this configuration in ethane. So far, we have examined only single sigma bonds. But how do carbon atoms form double bonds indicated by the structural formula for ethylene? To find out, let's first return to carbon in its ground state. As any good conjurer, carbon has another quantum trick up its sleeve. Voila, a new hybrid state. Notice that this hybrid model has a different structure than the hybrid model with the sp3 orbitals. It is this specific, different hybrid state that will explain the nature of the double bond. To understand how this hybrid state was formed, let's take carbon in its ground state and use an energy diagram, reminding ourselves that what we're assembling is pure hypothesis. Carbon contains 2 electrons in its 2s orbital and 2 electrons in its 2p orbitals. With a shot of energy, an electron in the 2s orbital is booted into a vacant 2p orbital. Simultaneously, the remaining 2s electron is promoted to a higher energy level as a pair of 2p electrons drop to this intermediate level. These hybridized orbitals are designated sp2, and their electrons are called sp2 electrons. The sp2 hybridized orbitals are oriented on the same plane at 120 degrees apart, whereas the remaining 2p orbital is aligned perpendicular to this plane. What must be emphasized is that the electron in the 2p orbital is at a slightly higher energy level than the electrons in the sp2 orbitals. This hybrid state model now illustrates the double bond phenomenon of ethylene. In the act of bonding, these 2 sp2 orbitals overlap to form the now familiar sigma bond. The remaining sp2 orbitals form sigma bonds with hydrogen. One final step remains. The electrons in the 2p orbitals meld in this saddle-shaped arrangement. Now don't let this hurt your head, because the electrons are about to pull their usual quantum stunt. They alternate above and below the plane. The overlap of carbon electrons in the p orbitals is called a pi bond. So, when we use the structural formula for any carbon-carbon double bond, we must remind ourselves that the double bond is composed of both a pi bond and a sigma bond. It is the site of the pi bond that is most vulnerable to chemical attack. Pi bonds are weaker than sigma bonds because the pi electrons are, on the average, farther from the nucleus than sigma electrons. In molecules like ethylene, the pi bond keeps the hydrogens of the 2 carbon atoms aligned in the same plane. As well as acting like a straitjacket in this case, pi electrons are adventurous in ways that exceeded even Kekule's dreams. In his vision, benzene formed double bonds in this manner. Quantum mechanics, however, amplifies his vision. It accepts in general his rigid sigma bonds. But the pi bonds would be locked in place by Kekulé's formula. Pi electrons instead escape their shackles Houdini-like. At a higher energy level than the electrons in the sp2 orbitals, they are not bound to specific pairs of carbons, but resonate in continuous rings. We've come a long way since Wohler declared that organic chemistry is a jungle. Out of the jungle has emerged the underlying architecture of carbon. And it's this architecture that provides science with a key to discovering over 1,000 new carbon compounds each year. As we explore some of the more useful compounds, plastics that reshape our culture, fuels that fire the engines of industry, synthetic fibers that support fashion and design. Don't be intimidated by the variety of formulas and models you will encounter. For example, in this type of space-filling model, we have depicted the overlap of the hybridized orbitals this way, so that carbon and hydrogen atoms clearly stand out. And the bonds are depicted as a definite overlap. Others argue a more realistic representation depicts the mutual absorption of the orbitals this way. Fine. When symbolizing molecules, chemists select the model which emphasizes that aspect of the molecular structure they wish to feature. Some even resort to childhood tinker toys. And when some atoms play a redundant role in a chemical reaction, just pull them off. In truth, space-filling models are not terribly useful beyond explaining the nature of bonding. With organic chemistry, we deal with macromolecules, and they would end up looking like a junkyard, when a structural formula is much easier to grasp. In science, the ultimate test of a model is whether it is useful, so simplicity is the dictum. More often than not, chemists are only interested in the reactive sites, or a potential reactive site on a molecule. This is the formula for benzoyl peroxide. With a hit of energy, we now convert it to two free radicals. The result is an unpaired electron, the reactive site on each radical. Chemists love shorthand, and so replace the superfluous atoms with the letter R. Because this is television, well, we take a little license as well. Our short form for the radical is a sphere, to which we attach a ravenous electron. Later in this series, we will explore the scavenging action of this radical in 3 dimensions, the real world of atoms and molecules.